Good morning, everybody, and welcome to this presentation of the ultra-thin precision microphone. My name is Lars Winberg, and I will guide you through this presentation. Practical point of view, the meeting will be approximately 45 minutes, and I have taken the liberty to mute all your microphones, so there will be no interference with the presentation. If you have any questions, whatever it is, you are welcome to use the chat functionality of this program, or you can write an email to me at lw@gras.com.dk. And you see a picture of me down there. It is my name is Lars Winberg, and I'm working as the business development manager for Gras. And my experience within acoustic, it is going more than 30 years back in time. So I hope you will enjoy the presentation, and I will immediately show you the agenda for today. So the 45 minutes will be divided into different sections. And first I will show you just a couple of slides, I think it is two, with an introduction of the Gras company. Then I will do a little bit basic aeroacoustic, and then talk about the aeroacoustic toolbox. And the majority of the presentation will be on our ultra-thin precision microphone, a brand new microphone family that I will show you what is the background, what is the abilities of this microphone type. So let's start up with the company overview. Gras, Sound and Vibration. This is the founder of the company. This is the pioneer Gunnar Rasmussen, and he started the company 26 years ago. So the name GR, it is actually the initials from his name, Gunnar Rasmussen Acoustic Society. So it is quite straightforward, the name, even though it is many people are asking what it is actually meaning. So it is Gunnar Rasmussen. Today we provide the widest range of measurement microphone and fixtures in the industry. So that means that we are developing microphones and sensors, acoustical sensors, but also a lot of fixtures that can be used for different test setups. So what you see in the background or on the picture up there, it is a headset test set or a fixture that can be used for different kinds of tests of headsets. Today, we are also a little bit more than 110 employees. We have a headquarters in Denmark, and we have business partners in more than 40 countries worldwide. So we are a true global company. And what I would like to stress is also that innovation has always been a key competence within Gras. And I will show you some of the examples what we have actually achieved over the years. So talking about aeroacoustics, we basically are focusing on two different industries. One industry, it is the NVH or the car industry, automotive industry, where aeroacoustics is getting more and more of interest due to electrical vehicles, and predominantly the wind noise is taking a more major role in the overall noise pattern. So we have supplied equipment to this industry for more than 25 years. We are suppliers to all the major OEMs and tier ones. And I've just taken some of the brands down here, but we have a long list of different brands that we're actually supplying today. What you see on the product side here, I've taken out two of some of the innovations that we have done lately, and this is the 146AE. This is a very versatile. You can make roughly 80–90% of all the measurements you are obliged to do for NVH testing for acoustics with this microphone. It is a microphone going up to 20 kilohertz, and it's a half inch, and you have all the facilities. You can do outdoor measurements, indoor measurements. You can do high temperature, low temperature measurements. And it is also totally watertight, this microphone. So it is really the most versatile microphone in the market today. To the left here, you see another microphone, which is called 147AX. And this microphone, it's a little bit different in form factor. So we have flattened out the preamplifier, and we have implemented a magnetic base on this one. So that means that you can do repeatable testing. You can mount it exactly on the same spot as the last measurement, and you will get exactly the same result. So you can do a before and after test, really simple with this magnetic base type of microphone. So this is one of the segments that we're addressing with the aeroacoustic microphones. The second area, it is the aerospace testing. And aerospace, there I've taken out some of the brands that we are supplying, or companies we are supplying. And I was a little bit surprised when I saw all the logos. It seems like blue is very popular amongst aerospace companies. So again, I've taken out some few products here, and I will show you this round plate here. This is a cooperation with NASA, and this is used for overflight testing, where you need to have a uniform response regardless of what sort of area you are putting this one on top. So this is according to all the international standards, and this is a unique product that we can offer to the industry. The other product here on the right-hand side, the strip here, I'll go through in the end of this presentation. Great. So let's go into the basic aeroacoustics. And you're probably more experienced in this than Gras is. So you know all the different issues and problems you have with this. But this is a picture showing, this is the wind speed here. There is a surface down here. You have a boundary layer that is building up. In the beginning, there is no aerodynamic noise, and you have a laminar boundary layer or a laminar flow. It is coming into a transition region, and then you're starting to get a turbulent boundary layer. And this turbulent boundary layer, this is where we are interested in actually quantifying the pressure variations, small, tiny pressure variations on top of the surface. And the reason why it is that noise is generated by this turbulent fluid motion, and noise is also generated by the aerodynamic forces. This is the small pressure variations here that is interacting with the surface here. The problem is that it's not so simple to actually do measurements in this area, because first of all, you are not supposed to disturb the flow in itself by the measurement. So everything that is sticking up here will influence the conditions, and therefore it will not be a perfect measurement. Secondly, sometimes this boundary layer thickness is really thin, and therefore it is very difficult to measure here. And if you have some sensors that are actually showing up on top here, you're not actually measuring what you're interested in. You're interested in the small pressure variation just on top of the surface. So this picture, it's a theoretical picture. If you are converting that into real life, this is a wing for an aircraft. This is the airflow. You have first a laminar flow, and then you have a transition area, and then you have a turbulent area here. And this is the point of interest that we're having. Great. A little bit of a wrap up also on different noise sources or acoustic sources or pressure sources. If you take a look at this picture here, the gray area here, you have the surface. And we have now mounted a microphone that is sticking up here. So we have a membrane that is 100% flush with the surface. and we have a flow over here. And what are we picking up from the different sources here now? First of all, if you have an acoustic source, and this could be the equivalent in the air situation, you are sitting in an aircraft, you are on the runway, and they have just started up the jet engines. Then, of course, you hear only the jet noise. So the red curve here is corresponding to an acoustical source, which in this case, it is the jet engines. So this is the only noise that you're hearing when you're taking off or just before you're taking off. And this is an acoustic pressure fluctuation or acoustic source. This acoustic source is propagating at the speed of sound. This is from your study books in quite straightforward. And then when you're coming up in the air, you actually have another predominant source, and that is the wind noise or the aerodynamic noise. And this is caused by the flow over the surface, and this is the boundary layer pressure fluctuations that I talked about in the previous slide. So now you have two sources. You have the jet engine and you have the air that is flowing over the surface. And this is a little bit of a different source because this is a aerodynamic noise or aerodynamic pressure variations. And these pressure variations, they propagate at the wind of the speed of wind or speed of the movement of the airplane. So when you do measurements in this area here, you can focus on the aerodynamic noise. Sorry, I was a little bit too quick here. You can focus on the aerodynamic noise, the external noise, which is the jet engine in this case, or a combination of the two. And some of the tricky parts of doing measurements here, it is the separation of the different sources. But there are different techniques for achieving the best possible result for this. So now I will take you to the next step here. And this is the same situation here. Now we have just removed the acoustic source. So there is no acoustic source. It is only wind-induced pressure variations now. So we have the plate here. We have a surface, and we have a microphone sticking up here. We have a diaphragm or a membrane that are totally flush on the surface. And we are measuring right now in this area here. What we see coming out of this measurement, it is the pressure variations as it is implied on the top of the surface here. What will happen if we are actually mounting a bigger microphone or a bigger microphone? This is a very tiny one. This might be a 1/8 inch of a microphone or a 1/4 inch of a microphone. If we are now putting a 1/2 inch microphone or even a 1 inch microphone, what is happening? Well, you can actually see here that the signal is the same, the output is lower. And the reason why it is lower, it is because the membrane or the diaphragm, the area of this one is actually averaging some of the signal coming in here. So you can see you have a tip or you have a dip at the same time. So that means that the membrane cannot swing in two directions at the same time, and therefore it is an averaging of the signal over the membrane, and you have a lower signal coming out. The third scenario here, it is with a product that we launched some 6-8 years back, and this is called the turbulence screen kit. Now we have taken the microphone here and we have recessed it a bit. And then we have mounted this turbulence screen kit in front of it. And this is actually enlarging the area even more here. So this is basically evening out or screening the wind flow noise. So dependent on the size of the membrane, you will actually get 3 different results out here. This is good to know. But what we are also going to discuss, or what we are going to discuss in the continuation of this presentation, this is a test where you have to drill a hole in a plate. So this is a destructive test. So if you don't like to do, or if you don't have the liberty to make a destructive test, maybe you have a side window of a car, and you are not really in a position where you have the time to do a blind window, drill some holes and mount a blind window in the car. Or you can have an in-flight testing of an aircraft where you don't have the liberty, or you can't take the liberty to drill a hole in the side. So in that case, we are using what we call surface mounted microphones. And these are, of course, of highest importance that they are not sticking up too far, because if they are sticking up too much, they will influence the measurement by having a sharp edge here. And secondly, if they are too high in profile, they might not be able to pick up the very small variations close to the surface. So therefore, it is leading us to a little bit of a wrap up. We can have what we call wall mounted or destructive testing, where you are having to drill a hole. Then we have a range of products that is fitting into this area. And we have a lot of sockets that we can offer. So you can mount it flush, 100% flush. We even have a type of microphone called flush mounted microphones, which has a slightly different form factor, making it easier to mount it in a scale model, or in a DUT, or in the wall of a wind tunnel or so. What we also have, it is for non-destructive testing. There we have had this microphone for some time. This is a surface microphone, which has a profile height of 2.5 millimeter. And then we are now introducing what we call the UTP, the ultra thin precision microphones. And they are slightly smaller. They are only 1 millimeter profile height. So I will focus on this new release that we have done a couple of days ago. And you will see it is actually a family of products. And I'll go through the different parameters of the sensors. But first, I would like to show you the background for it. We started up this process of trying to find out how to build smaller microphones some 5-6 years ago. And we fastly found out that with the current technology that we had, it was simply not possible to actually make them smaller. And I will show you the reason why. So therefore, we have patented the method that we are making these microphones. And in the patent, it is stated, the invention relates to a surface mountable condenser microphone comprising a diaphragm spaced by a spacer from a conductive capacitor layer arranged on a surface of a backplate. This is not very simple to understand, and I will guide you through in some easier words what we have done. So first of all, going back to a standard microphone, this is a traditional condenser microphone. So regardless of what brand you're buying, this is how they are built up. You have a casing, and you have an insulator, and on the insulator, it is mounted a backplate. And then on top here, you have a diaphragm or a membrane on top here. So how it is working? Well, it's quite simple. If you take a look here, it is a condenser microphone. So the principle of this microphone, it is exactly the same as a capacitor. So you have a air gap in between the backplate and the diaphragm, and you're putting a voltage on one of the sides. And then when the distance between the backplate and the membrane is different, it will be reading out a signal on the insulator, or sorry, on the backplate on the bottom here. So it will work if you're changing the distance between the backplate and the membrane. It will come out a signal out of this one that is corresponding to the vibration or the pressure variations on the membrane. So this is a traditional condenser microphone. Why is it not possible to make them tiny, tiny, small packages? Well, the way it is manufactured, it is basically a mechanical construction, this. So we have to be very careful when we're mounting them, because it is a mechanical ring here that we call a spacer that we have to put in order to control the distance between the diaphragm and the backplate. And it has to be with very high tolerances. So it is really, really necessary to do this very carefully. And this is not simple to actually go down in size. So we have been trying for years and years, and we have found that the physical limit for actually doing this in a mechanical way, it is roughly 2.5 millimeter. And that is the reason why our surface microphone, it is 2.5 millimeter. This is built exactly on the same principle as this one. So what we started to do, we changed the way that we were building them. We are using exactly the same parts. So we also have a diaphragm, we have a backplate, and we have everything that you see on the upper picture here. But this is a picture taken directly from the patent, and it is showing that it is a lot more complicated here. But what we have done, we have mounted the backplate here, directly on a surface. And then we use a chemical process to build a spacer between the surface and the membrane. So we can, in a chemical way, control the distance between the backplate, or sorry, the surface, and where we are putting the membrane on top. It is still an air-damped membrane, so the functionality, the way it is working, it is exactly the same as the top picture here, but it is just much, much smaller. So our tiny little package here, the size, it is 1 millimeters times 9 millimeters times 18 millimeter. This is the sensor, and you see the sensor diaphragm here. And this is also including a preamplifier with this size. So it is a tiny, tiny microphone. And I'll point out some of the highlights of this one. First of all, the low profile. I told you before that doing aeroacoustic measurements, it is absolutely crucial to go as close to the surface as possible. One reason I've said it is that it is not influencing the flow over the area. Secondly, you have to stay within the boundary layer. And thirdly, that I haven't discussed so much, it is that if you would like to do a correlation with a model, a CFD model, you have to do exactly the same measurement as it is set up in the model. So the closer you are coming to the surface, the more equal you'll get the results in a experimental test and in the simulation package. So the low profile is absolutely a key to this sensor. And everybody have probably had an American $quarter in their pocket. This is the size if you're flipping it to the side, and this is the size of the sensor. So it is roughly half size of a quarter pound. Oh, sorry, $quarter. So what do we have here? We actually have a 1/4-inch condenser microphone membrane on top here, and you see it is flashing up here. It is the membrane. We have a very small footprint, 9 × 80, which means that it is suitable for also doing a lot of measurements in small cavities, small areas. We have implemented CCP or ICP or IECP technology for easy integration with existing hardware. So this means that you take the single cable going out here, you plug it into your analyzer, and you're up running immediately. You don't need to mingle around with the pressure tubes or anything like that. You just plug it in and you're up running. And it is also having TEDS functionality for easy sensor identification. transducer electronic data sheet. So all that is built into the design, and we have 4 different versions. This is a high pressure version, and this high pressure version is going plus minus 3 decibel up to 31.5 kilohertz, and it is having a highest sound pressure level, the capacity of 184 decibel. So the second one, it is a medium pressure. It is going up to a little bit higher frequency span or a frequency range. It is going up to 70 kilohertz, and it is also having a little bit lower noise floor, 54 decibel, and going up to 170 decibel. Then we have taken this medium pressure version and we have done predefined line arrays. And we have taken 2 different line arrays, and this is a 4-channel line array and it is an 8-channel line array. So we have already configured this line array, and what is the advantage of having it already predefined? It is that for once you have only 1 cable going out from this one. So in this case, an 8-channel strip, you have 1 cable you have to fix on your model before you're running it into a wind tunnel, for example. And this single cable is between 3 and 5 meters. And then it is going to a breakout box, and then you have 8 individual cables, 1 for each channel of your analyzer going out from there. So it makes it very easy when you're mounting it. You might say that, well, it seems like it's a good idea to have a strip like that, but I'm not sure whether this geometry is fitting my application. Well, in that case, we can also do custom design. So that means that if you have some real or interest in another spacing between the microphones, we are eager to discuss the project with you and come up with a proposal. So the industry fit with these new sensors, this is a little bit of a view on that. So if we take automotive wind tunnel testing, typically they would be interested in frequency ranges up to maybe 13 kilohertz. I've taken the liberty to put 20 kilohertz in here, and probably background noise from the wind tunnel around 60, 65, maybe 70, and then up to 120. So these medium pressure sensors are well suited or fitted for the automotive wind tunnel testing. They have a frequency range of up to 70 kilohertz, so it's well within the range here, and they have a 54 to 170 decibel. Well within here as well. For the aerospace, there are 1 application for in-flight testing, and now you have clustered the sensors on the side of the aircraft, and then we are recommending to use a high pressure version, and this is going up to 184 decibel, and this is probably most suitable because you can expect quite high noise level. I don't expect you to be able to see 180 decibel, probably around 170 or so. So this will be well within the limits for that application. For the aerospace wind tunnel testing, there you're normally operating a lot more with the components or with scale models, and scale models require higher frequency range, which means that the medium pressure will be the preferred option for that. So in order to wrap up a little bit, the LA48LA, it's the high pressure version, which is for more demanding applications, and then you have the medium pressure that will take the rest, the majority of the testing. So this is a little bit of a wrap up of that. You see this is a mount on the side of an aircraft. Here you have the high pressure version, the 184 decibel, 15 to 31.5 kilohertz, and this is for in-flight engine rig test and so on. And then you have for the wind tunnel, you can use the preferably the medium pressure versions that is going up to a higher frequency range. For the car industry, this is the example here. You have one sensor mounted on the side window up here, and you see the result here. This is probably number 2 and not number 4. And you have the mounting of the sensor here, and this is a medium pressure version. Then you have the possibility to put in the line arrays, where it is very, very fast to mount. As you can see here on the side of the car, you see it has been taped on directly on the curved area here, and there's only one cable sticking out, which means that it is extremely easy to fix this. So some of the features, as I said before, the low profile, it is the key to do good measurements. Secondly, we are selling what we call a flow optimized fairing. And this fairing, it is evening out the sharp edge on the microphone here. So you're using this holder or fairing to actually fixate the microphone on the surface. So what you do, you take a double-sided tape and you're taping it to the surface. And then you use this slot here to slide in the sensor. It goes into a locking mechanism, and then it is locked in the holder, and you can do the measurement. And after the measurement, you just retract it again. And then for the next test, maybe 2 weeks later, you can still use the same position, which means that you can have a comparable measurement 2 weeks after, using exactly the same position, using exactly the same mounting fairing. This fairing has an angle of 7.5 degrees, which is ensuring that there is no flow-induced problems here. So I'm also stressing quality data, and you say quality data. Well, I'm always getting quality data, but if you're thinking here, this is a condenser microphone, which means that it is coming with individual calibration charts. So all the microphone has been calibrated in a calibration lab before it is shipped to our customers. They are getting a individual calibration chart, and they are including TED's functionality. So I have the electronic data sheet as well. So, and then, as I said before, it has a simple connection. So there's only one cable. You connect it to your analyzer, and it is you don't need to have any power supply or anything like that. It is also using the TED's functionality, as I said. So a little bit of a wrap up on the mounting principle. You fix the sensor, and this test, by the way, it is not a aeroacoustic test in a common sense here. This is, I think it is mounted in a small cavity on a car. So you mount the holder or the fairing, and then you are sliding in the sensor into the locking mechanism here, and it will say click. And when it has clicked, then it is fixed. And then you can extract it with a small pin or a paper clip, because it's a small hole here that you can actually put a pin in and you can extract it. So you have a very secure mounting by the fairing. Here is the same equivalent with the strip. Now you can see you have the strip, you have the blue area here where it is supposed that you should use tape, masking tape, and you use this masking tape, and then you are mounting it in a very short time. So I'll show you a small, I'll show you the movie after this slide here. What we have also built in this concept, in this family, it is a adapter for the calibrator. So even if you have mounted a microphone on a slightly curved area, you can easily use this adapter, calibration adapter, to verify that the system is okay before you're doing the measurement. So what you do, you can see here, it is consisting of a small cushion, and this cushion has some distance legs. So you're pushing it down gently over the sensor. And then when the cavity is stable, the volume, then it will turn green here. And then you can start the calibration with 250 Hertz or 1 kilohertz in the normal way, how you're normally calibrating microphones. So this is how we do it in field. Of course, we also have a full calibration adapter set. Sorry for that. So you can do all kinds of calibrations in the Cal Lab. So all in all, it's a very strong concept. And I will show you how you are fixing it with the strip, and you can take a look at the watch and see how long time it actually takes to mount the microphones. Here you see you're finding the right position. You are just using the tape. You are fixing it like this. And this area, it's a slightly curved area, so it doesn't matter. You're fixing the cable. It's one single cable coming out to the breakout box, or a breakout cable, I should say, because it's not really a box. It's only a cable. So then you're fixing it on the sides here. And when that is done, you're ready for the test. So just to do a little bit of a retest or move it a little bit, you just take it off and you fix it on another spot. So this is really, really efficient. So apart from the Aeroacoustics, you can also do what we call the cavity testing. So here we have on the tailgate of a car, we are interested to quantify the noise down in this cavity here. And what you can do, you can mount a sensor fairing, you can fix or you can mount the microphone, and then you close the tailgate, and then you can do quantification of the noise inside this by taping some areas, and then see what is the difference and see where do you have any spots that you need to focus on. So in order to wrap up, we call this 3 words: flat, fast, and precise. Flat because it is really, really essential not to disturb the turbulent flow. Fast because we have done the line array, 1 cable out, leave the fairing, use it again. CCP, TEDS, everything is making it so simple to do your measurement. And precise, it is giving quality data, because this is based on a condenser microphone having individual calibration charts, and you can validate the measurement chain before and after any measurement. So all in all, flat, fast, and precise. If you're having questions about price and availability, you are welcome to contact our local GRAS representative in your country, and you can have an overview that is available on www.gras.dk. If you have any questions, as I said before, you can write that in the chat function of this presentation, or you can send it on a mail to lw@gras.dk, and I will answer you individually. So I also promised you some feedback from customers, and I have one more slide in this presentation, and I will leave it on for the next 5-10 minutes. And if you're interested, you can read what they have said. And otherwise, I would like to wish you a have a good day. And thank you so much for the attention. And I hope that you have learned something new about how easy it is to do aeroacoustic good measurements. Thank you very much, and hope to see you in real life soon. Thank you very much. Bye-bye.